the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 6, Elastic Plastic Analysis of Torsion, Part 6. In this section, I'm going to present to you a plastic analysis of torsion of prismatic bars. So far, we have talked a lot about the torsion of prismatic bars, but all of what we have said has been concentrated or focused on elastic analysis of prismatic bars. Although we elaborated on many different techniques and interesting techniques, but they have all been for the elastic analysis. And here we are going to present to you plastic analysis of torsion of prismatic bars. Here again we are going to use an analogy, a very simple analogy called sand hill. Now consider a circular cross section such as this. That is the cross section of the prismatic bar. And what we are going to do with this sand hill analogy, what is the analogy here? Well, if you have some volume of sands and you pour it on the cross section, supposing we have a cross section like that, this cross section you can inscribe it on anything, on a cardboard or anything, and put some base underneath and pour the sand on the cross section. Okay, after a while the sand piles up on the cross section and you will see a shape like this, a conical shape like this, because the base is circular. If the base is different shape, then you won't get a cone, you will get different geometries. Okay, so by sand hill we mean that we put sands on the cross section and pile it up until we reach a point that no more pile up is formed. Okay, so there is a certain volume of sand on top of the circle or cross section. Now for circular cross section, K, which is the yield strength, K is the yield strength in shear, because when we increase the torsional torque to reach the plastic region, if we take it as rigid plastic, perfectly plastic, in fact, not rigid plastic, perfectly plastic, then we will have, once we reach the yield strength, then in the stress strain curve we will have a straight line which is parallel to the horizontal line. Okay, so that's the K, that's the yield strength in shear. Now we say that this is proportional or equivalent to the gradient of this sand hill. Okay, now where do we get this idea from? Again, here, in fact, sand hill, I will explain to you in a minute where we get this idea. Okay, how did we reach to this conclusion? I will explain to you in a minute. For the time being, take it granted that this is true. Also, the volume of this pile up of this cone is a third of pi a squared h, which is the volume of a cone. And we said before that T is equivalent to 2V in the membrane analogy, and therefore T we could put here, instead of H over A we put K, and we get this T is equal to this. Okay, and similarly for a triangular cross section like that, we don't get a cone but we get a pile up like this, which is a pyramid, and therefore we can have the gradients on the side of this pyramid and also the volumes as well. And using the same analogy, K is H over a third of A root 3, because all the sides are symmetrical, and the volume is this, so we use this substitute for H in here, and we get T equal to 2/3 of A cube K. So very simple. You can see that the torque required to yield this prismatic bar is obtained very easily and is equal to that. Here also it is obtained very easily. Now let's take a rectangular section and use the same concept to see what we can do here. Okay, so this is a rectangular section, so our prismatic bar has a rectangular section, and if we look at the top, the plane view, we see this view. Okay, so that is this bit here, and this bit here is that. So I can divide this into two areas, area 1 and area 2. Okay, these are the dimensions of this pyramid, and K here is 2H over A, that is the gradient here, and also we can calculate the volume of this pyramid like that. And so if we use this and substitute here for H, we can get the torque required to bring this bar into the plastic yielding. Now for the square section, of course, this A and B are equal, and T becomes A cube K over 3. Well, I have shown here how I have calculated these things. We can use this section like that. That's A over 2, that's A over 2, and that's B. So that's section 1, and that's section 2. So that the volume using these areas can be calculated like that for section 1 and section 2 times 2. Because we have one section 1 is here, section 2 is here, section 1 is here, so times 2 becomes the volume. Okay, now then let's see what else we could do. For the rectangular section also we could use another method to calculate T. What is this method? This method is that we say that if the material in the prismatic bar with the rectangular section reaches the yield point, then the force acting on the material is the yield shear stress times the area 1, and also the area 2 yield shear stress times area 2. Okay, these are the forces acting on area 1 and area 2. Then multiplying these forces by the arm gives you the moment. And what is this arm or radius? If we take G1, the center of gravity, or the centroid of ABCD, okay, for the area 1, then force must act on the centroid G1, so OG1 times the force gives us the moment or torque. Also on area 2 as well, if we take G2 as the centroid of this triangle, then OG2 times the force gives us the moment or torque. But because we have taken only half of the area, so that's why we write T over 2. And now area 1, area 1, we can calculate it from here. As you can see, I have calculated area 1, and also simplifying it to that, and also area 2 can calculate it from this simple triangle. And therefore, substituting area here and there, we get this relationship, and simplifying it, I get the same answer as before. Okay, so that's another way of doing it. I'm going to show you some pictures here. First of all, I have this rectangular cross section like before, and what I have done in here, this red one and the blue one. Now the red one is the elastic boundary. In fact, is the elastic analysis using a membrane. Remember, we put a membrane in here on top of this section. In the section, if we cut it out, we get a hollow area underneath, and we put pressure, and the membrane bulges up. Okay, and we get something like that. Now in here, we are saying that this is some kind of a roof we have made on top of this rectangular section, as I showed in the previous slide. And I'm saying that this elastic boundary. Okay, so if I put pressure on this elastic boundary, what happens? So far we are in the elastic region, but if we go ahead and increase the pressure, you can see some of these areas have become plastic regions, elastic regions. Why they have become plastic? Because this membrane touches the roof. Okay, touches the roof, and so we get some part of it becomes plastic. It cannot move further away from the roof. Okay, and as we increase this pressure further, this plastic area becomes more and more, and we reach more plastic areas as we increase the pressure. You see, this membrane touches the roof now, so only small areas are elastic. These green areas are plastic, and finally we reach a stage that we increase the pressure so much that we reach all the areas become plastic, complete plasticity. Now that idea that I presented at the beginning of this part, and said that I will explain this idea later. Why did we take K equal to the gradient of this roof? Why did we do that? In fact, we have taken this from the membrane analogy. In the membrane analogy, we know that the stress is related to the gradient of this membrane at different directions. Now, if we forget about this roof and just have a look at this membrane, as you increase the pressure, this membrane can go and can bulge as much as you increase the pressure. But there is a limit for it. Where is the limit? If that gradient, which is the stress, reaches the yield strength, that is the limit. Okay? So that's what we have done. We have taken the limit. This is the limit, that is the limit, that is the limit. We have taken the limit for the growth of the membrane, and we have put that limit equal to K. So that idea at the beginning, which I didn't explain and said that you take it for granted, is completely explained here. It's very clear now that this membrane cannot move or cannot go up or cannot bulge from more than a limit. and that limit is the yield strength, and the yield strength obviously must be the gradient which is equal to the stress. So that's what we have taken this sandhill analogy, that is the source of the concept of the sandhill analogy. Okay, and so you can see here that if I put this membrane on here and put pressure underneath, it will bulge up and it will touch these areas, and these areas have a gradient of K. So that's how we make these roofs, okay, or sides on top of the cross section. It's not arbitrary. The gradients must be equal to K, because the elastic region must not grow more than the strength of the material, yield strength of the material. So we use these sides, these areas, flat areas with constant gradient equal to K.